This is mini lecture number 12. And in today's lecture, we're going to do a bit of a ramp up. We're going to basically cover a few important concepts. We're going to start with talking about practical sources, practical voltage and current sources. And then we're going to move on to source transformations, equivalency between current and voltage sources. And then we're going to find out, we're going to terminate this mini lecture by looking at maximum power transfer, which is a very practical, elegant way to look at engineering problems, if you will. Some of those things will provide some proof. You are not expected to be able to prove, although I think the elegance of the method sometimes might be of interest to you. Plus, there is an essence of practicality in what we're covering today. The title of the lecture being Practical Sources should tell you that. So let me share some PowerPoint and we'll begin there. There we go. So we're going to start with the voltage source. So probably the most common voltage source we can think of is either your 9-volt battery or your car battery. So when we think of a voltage source, we think of a source that's keeping a set voltage. In the case of your car battery, it's keeping a 12 volt between the two terminals, the red and the black terminals. The red is the positive, the black is the negative, so it maintains a potential difference of 12 volt, and we assume that's kind of an ideal. Of course, when we put that symbol that I'm showing you to here, this is really assuming an ideal case. That is, doesn't matter what you connect to the source, you're going to have 12 volt, if it is 12 volt or 9 volt. The reality, things are not ideal in real life. So in this particular lecture, we're going to look at a little bit more practical things. What is a practical source model? What is a practical voltage source model? When we look at this particular configuration, let me clear this up a little bit. We look at this particular configuration. If we connect the load, let's say a resistor to it. Now, what happens if you actually short circuit the two terminals of the voltage source? We know that from our car battery, if we take like a jumper cable and we connect them together, you get a spark. So we know we draw a large amount of current if you short circuit the two terminals. But this particular model seems to imply that we would be drawing an infinite amount of current. Well, no such thing as an infinite anything. So clearly this model is an ideal model. So we need to look at something a little bit more representative of real life. So today we're going to introduce a practical source model for the voltage source. The practical source model for the voltage source is an ideal voltage, which we call Vs here, in series with what we call a source resistance, Rs. Okay. In real life, everything has resistance. There is no such thing as an ideal anything, an ideal cable, an ideal source. Everything has a resistance here. So we lump that resistance into Rs here. And that actually is a very accurate source model. Okay. So Rs is called the internal source, the internal resistance of the source. So that's the practical source model. If we actually now go ahead and connect a load resistance, some resistance RL, you can see that the current to that load resistance is going to be, by Ohm's law, it's going to be Vs divided by the sum of the resistance, RL plus Rs. So even in the case when RL is set to 0, in the case that we short circuit the two terminals of a source, you do realize that you will draw a large amount of current, but not an infinite current. The maximum current you can draw is Vs over Rs if RL is actually set to 0. So you will draw a large current, but not an infinite current. What you see also is that the voltage VL, when you connect a particular load, it's going to be less than the voltage Vs by virtue of voltage division. So this is actually a very accurate and a practical representation of a voltage source. Okay. So this is not, just to make sure you know this is not a practical model for the voltage source. This actually, this resistance RS in parallel with an ideal voltage source does nothing essentially to the model. Okay, so again, back to this is the practical voltage source model. And it is an ideal voltage source in series with a source resistance. So let's look at for the current source then. So for the current source, we've been using, again, an ideal current source model, which what a current source is supposed to do is just like a voltage source maintain a set voltage across the terminal, current source maintain a set current. In reality, current source and voltage source are one in the same, except one seeks to maintain a set voltage, one or in the current source seeks to maintain a set current. So in this particular ideal model here, again, if I connect the resistor RL to the current source, you can see what happens if RL becomes very large. Then all of a sudden, my voltage across the resistance would also become very large. So if I just open it up, that is disconnect everything, would implies an infinite resistance. So if I set RL to infinity, which means leaving it open, that implies that I have an infinite voltage across the current source. Not a realistic picture of anything in real life. So we need a practical model for the current source as well. And the practical model for the current source is an ideal current source, IS, in parallel with the source resistance. Okay, so that's the practical current source model. And if you connect the resistor RL to it, you're going to see that the current you get is slightly less than IS. Okay, slightly less than IS. It depends obviously on the resistor RS. Okay, so that's the current that you would get onto some RL. But if you just leave it open, if RL goes to infinity, then the voltage across RL will basically be IS times RS. So it's not infinite, which makes sense. You don't get an infinite voltage source just by disconnecting the load. So these are the two models here. The voltage source model is a series ideal voltage source in series with the source resistance. And the practical current source model is an ideal current source in parallel with the source resistance. So these are going to become a little bit more tangible, if you will, in the next week or two, in the next few lectures, as we cover the Thevenin and Norton models. So the last question we're going to address, essentially, again, just a last note here, given that RS in parallel, the larger resistor draws the least current here. So if RS is a small resistance, essentially you're going to have most current going to RS. If RS is a large resistance, most current is going to be going to RL. Okay. So the last comment that we want to address here is source transformations. Okay. In other words, we want to look at case where these two practical sources, on the left, you have the practical voltage sources. On the right, you have the practical current sources, current source model. We want to see under what conditions are they equivalent. Okay. This is what we call source transformation here. And when we mean equivalent, we mean if we connect the same load, just like I'm showing here, the load doesn't see any difference. It sees the same voltage and the same current coming to it. That's usually what it would mean, that it would be equivalent. Okay. So in terms of math, we basically would be saying that the voltage V1 is equal to the voltage V2 down there on the right. And the current I1 on the top should be equal to the current I2 in order for the load to see exactly the same situation. It sees both the same voltage and the same current under what circumstance that occurs. And we can show, you're not expected to prove this. This is essentially knowledge that I'd like you to at least to be aware of, but we will not, this is not something at the engineering 17 level that we would ask you to prove source transformation. Okay, for V1 equal to V2, we can show that that happens when these conditions are met. That is, the two resistance are equal, RS equal to RG, and the voltage and the current source are related by RG times IS. Okay, so this implies that these two circuits are perfectly equivalent. So that's the case here. That means we can remove one and replace it by the other, and the external circuit would not see a difference. This is what we call source transformation, something that, so this particular page you need to know. You need to know the practical source model for the voltage source, which is right here, the practical source model for the current source, which is right here, and under what circumstance are they equivalent. And they're equivalent when the resistance of both sources are the same, and the voltage and the current source are related by this relationship. So this you need to know. No expectation that you should be able to prove what we have here. Okay, so that concludes again introducing practical sources. They're going to play a major role over the next 2 weeks of content of this class. And also the source transformation has some modest application in circuits analysis. And I say modest, really modest. Okay. So the last part of this mini lecture we're going to look at, it's a really one of my favorite favorite lecture, is essentially the maximum power transfer. Okay, so I want to spend a little bit of time introducing the topic, giving you a practical feel. So in electrical engineering, it's always a power supplier providing power to a paying customer. Now, that has many forms in real life. If you work in the power industry, you're looking at the utility company sending power to a neighborhood, to a city, to some large consumer. So we're talking about megawatts. So when you see those power lines, they're carrying a lot of wattage, essentially from a supplier to a particular set of customer. So we're not talking small power, we're talking a large amount of power. So it is crucial, though, if I make the case earlier that this particular voltage source model represent a practical source model, and it does, okay? So this then would represent the paying customer. The load RL would present the paying customer. From the work that we've been doing over in recent lectures, you can probably surmise that the power that VS produces, that the voltage source VS produces, is going to be distributed in the power that this RS absorb, plus the power that this RL absorb. So what we are saying here is that whatever power that source produce is going to be basically distributed between its own resistance and the paying customer. It suffices to say it's really important to maximize the power that the paying customer is absorbing. Because if you don't maximize the power in RL, right here, the paying customer, you then burning your own power, which is highly inefficient. So the question of power maximization is a very elegant engineering problem that's addressed in multiple ways in electrical engineering. Again, if you're the power industry, we're talking about sending megawatts to a neighborhood. So that's important because whatever power you're not sending to the neighborhood, you're burning yourself. That's why you see those fans in those generators, because they're burning their own power. Okay. If you're working in the cellular, in the communication industry, we're not talking megawatts in communication. We're often talking milliwatts. So we're talking a small amount of power. It's equally important to send the most power to the paying customer, because there's not much power out there. They're talking about a small amount of power. So whatever power we have, we want to maximize that the paying customer receive it. So this is a really fundamental and interesting, and I think elegant engineering problem. And I am basically, again, we talk about the situation in communications, in which case you have an antenna that's sending power out, and then you have a receiving antenna that's receiving the power. So you want to maximize that, and because you don't have a ton of power coming your way. And then, of course, utility companies, again, face that same situation, but dealing with much larger amount of power. So I'm going to go to the document camera here, and I want to talk a little bit. I'm going to bring your calculus in play, okay? I'm going to bring your calculus in play to give you a different feel, a different and intuitive feel for this problem before we go solve it, okay? So if you give me a chance here, let me just bring the document camera, and hopefully it will cooperate and not crash. Okay, here's a document camera here. And I'm going to start the discussion here by saying to you, okay, let's assume I have a function, f of x. Okay, and let's assume the function looks like something like this. Okay, some function. So clearly what I'm drawing here, essentially, it has a maximum here. And I ask you, where is the function f a maximum? Okay. If I ask you that, you probably, if you remember your basic calculus, you're going to tell me it's right here. Right, what I have there, let's call it x of m. Okay. Specifically, it's where the derivative of x, of f with respect to x is equal to 0. That is the slope of x, of f. Okay. So in other words, we're looking at where the slope is 0. So the function is changing from a positive slope here to a negative slope. So that is where the function is maximum right here. Okay. So that is a standard thing, how we find the point of maximum here. And furthermore, this value here is f at xm. The function x evaluated at the point xm where it is maximum value. So this is the way we calculate how a function is maximum based on your basic calculus. So I'm going to take that calculus concept that you have, and then I'm going to say, okay, let's look at VS, RS. This is a practical source model. So this is your utility company. Okay, so the practical source model here. And then I connect the load RL. Okay, connect the load RL to it. And then I ask, what value of RL would maximize the power dissipated in RL? So you can kind of see the analogy between these two. You can see the analogy between, again, this problem here, which is a calculus problem that we've solved in our calculus class, and this really elegant engineering problem that we solve, that we are trying to solve here. Okay, so what are we trying to do here? Again, here we're talking about maximizing f. Here we're talking about maximize, let's say, the power L, which is power in the resistor. Okay, that's what we're talking about here. All right, and here, when we maximize f, we vary x. Here we vary RL. Okay, so in many respects here, this is very analogous to f, and this is very analogous to x. How's that? Again, let's resume the recording here. So we're looking at, again, varying RL so that the power that RL receive is maximum. So we could essentially look at RL as x, as to compare to the derivative problem in your calculus class, and PL being the function f. So if I look at the current here, that is IL. So what is IL? IL is VS divided by RS plus RL by Ohm's law. That's the current IL. And then what is the power RL? The power in RL. It's RL times IL squared. So I can write this as RL times VS over RS plus RL squared. So that's the power. So I'm trying to maximize this with respect to RL. I can almost write this as F is equal to X times VS RS plus X. I can almost do this, and then I'm going to look at df dx equal to 0. Okay, and I'm going to solve for X and solve for X, which is, in essence, I'm solving again for RL. My RL is my X. So this is essentially a very elegant engineering problem because it really addresses the consumer base power generation. We are sending power to a paying customer from a practical source model. And we're looking at, again, the power in the resistor RL, which represent here our load, our paying customer. And then we're going to do so by doing the derivative. So when we do this, what are we doing here? This means doing the derivative of PRL over RL. It's the same thing. So this is the same thing as this. Okay. So if I do that here, so what am I going to do here? I'm going to differentiate this with respect to RL. Okay. So this is essentially, again, PL is RL VS squared over RS plus RL squared. Okay. So remember, when we do this, everything is constant except RL. RL is my X. Okay. So the derivative of PL with respect to RL, derivative of the essentially a ratio, the derivative of the top multiplied by the bottom, so VS squared times RS plus RL to the fourth. I'm sorry, RL squared minus the derivative of the bottom minus 2 times RS plus RL times the top times RL VS squared over the bottom squared. Okay, so that's what we're looking at here. All right, and then we're going to set this to 0 and solve for RL. Okay, so this is, you can see how elegant this is. And again, the expectation is not for you to do this, to essentially to memorize this. It's just to give you a feel of the engineering challenge that exists when we have a practical source model connected to a paying load, where we're trying to minimize the power the source eats up itself and send more power to a paying customer. So I'm going to leave the document camera and go back to the PowerPoint just to show you the end result of that. So I'm not showing you the circuit anymore, but I'm hoping you have it in your mind here. So this is the power function PL, and I'm writing it in terms of what I had written here. And my challenge is to take the derivative of PL with respect to RL and set it to 0 and solve for RL values. That gives me that. So this is the derivative that I found by, again, the derivative of the top multiplied by the bottom minus the derivative of the bottom multiplied by the top. So if I'm setting to 0, the denominator doesn't matter. So I'm basically going to set the numerator here to 0. Okay, and that's what you see here. I'm setting the numerator to 0. And since real life RS is not 0 and RL is not 0, so this particular situation occurs when RS is equal to RL. That's a fundamental, essentially, response here to have that. Under the best circumstance, half of the power that the source puts out is going to be dissipated by itself, and half of the power is going to be sent to a paying customer under the best circumstance. So you can imagine how you do not want to operate under less than ideal circumstance, under less than maximum situation, where you'll be eating even more power than half, because at best case scenario, you're actually burning half of your power, and then the paying customer is getting half. Again, when that occurs, we can show that the maximum power that the load would dissipate is VS squared over 4RL when RL is equal to RS. Okay. So that concludes the maximum power. The expectation is not for you to memorize this, but I just wanted to give you an engineering feeling of the challenges and how systems work, particularly how the limitations of having to essentially generate power and burning your own power, being mindful of power transfer. It's really a fundamental engineering concept.